everyone, I wanted to let you know there's software you could install on your computer that has all the software I'm going to show you today, but you're not required in any way to do this. This is just really for your own edification, and I thought it would make it easier for you than having to download it off the internet, which is available, and you'll see in the slides. So you could just follow along with me. The first hour, we're gonna spend a lot of time with the theory of agents and how it relates to FHIR. And then the second hour, and we'll have a break, I will do a lot of demos and give you a much more interactive feel of how to do this, okay? So good afternoon, thanks for joining us. My name's Patrick Jamieson, and I'm from InterSystems. I'm mostly involved in FHIR education these days. And in this workshop, what I'm hoping to do is show you how Agentic AI can move beyond what you've probably been using it for a while, text generation, putting in prompts and getting answers. You could work with real healthcare data and real healthcare systems, and that's what I hope to show you. The key idea is that LLMs become much more useful when they could reason, call tools, retrieve data, and take the next step based on evidence. That's what we'll see. FHIR gives us a standard clinical data layer for doing this, and over the next 2 hours, I think you're going to see how all these concepts relate. Before we begin, just a quick note, there's these early access programs I want to make you aware of. If you're interested, you should click on this QR code, which you could find throughout the conference, and sign up for one of these programs. And we do value your feedback. So at the end, I would urge you to take the session survey, and this is what helps us make these programs better over time. So the first half of this workshop is going to build a conceptual foundation for the next part of the workshop. We're going to look at why Agentic AI and FHIR fit together and clarify the difference between an LLM, a workflow, and an agent. From there, we're going to talk about why FHIR becomes such a useful knowledge layer and why terminology normalization is often the hardest part of the whole system. I'm going to then preview at the end of the first hour the FHIR summarizer architecture, so you have a very good mental model before we move into the demos. We will walk through the tools the agent uses against the FHIR repository. And the FHIR repository I'm using is the InterSystems FHIR repository community edition. So you don't need to buy anything to get this to work. We will also end the workshop with safety, design patterns, production concerns, because this demo is not the end of the story. Everything I'm showing you today is reproducible. You have all the software that in your hands that I'm using. It's an open repository. It's not closed. The agent framework, the Docker-based environment for Iris for Health, it's all very straightforward, and I have given you the setup instructions. But I want to emphasize, you don't need to worry about any of that today. If you can't get it to work, and we have some proctors around the room that could help you. If you can't get it to work, that's totally okay. You can watch the demos that I'm going to show you. Same environment. Some people have problems installing the FHIR server in Iris for Health. I've created some videos, and you could look at these links later. That will help you install it when you go home if you are having problems installing anything in terms of this software. So let's start off with why Agentic AI and FHIR. Why does it matter? Well, we really need to understand why healthcare is such a compelling use case for agentic systems. It's not just a flash in the pan. FHIR is a great fit for the data layer with agent systems. Healthcare data is highly structured, but that does not make it easy to use. If you've used FHIR, how many of you have used FHIR in the past? How many are FHIR developers? So I see 3, 4. Well, I want to let you know that FHIR is a great standard, but it is somewhat complex to learn. And agents, I think, make it a lot easier for you to use a FHIR repository. But a patient record is not one document, nor is it one table. It is a graph, and you'll see it soon, of clinical facts accumulated over time. That is why interoperability alone is not enough. FHIR helps standardize access to data, but someone or something still has to interpret what matters in context. LLMs are excellent at language tasks, and I think everyone here knows that. But on their own, they're not enough for healthcare workflows. They do not query FHIR servers by themselves. They do not transverse complex clinical relationships by themselves, and they do not reliably maintain structured context across hundreds of resources. Most importantly, they do not inherently know when an action is too risky to automate. That's a human judgment issue. So the lesson is simple. LLM models are powerful, but the system around the LLM model is what makes it useful in healthcare. Agentic AI changes the role of the model. Instead of being the entire application, the model becomes the reasoning engine inside a larger system. It can help plan, choose tools, retrieve external data, inspect results, and continue until it reaches a goal. The shift matters because healthcare work is rarely a one-step text problem. It's usually a sequence of retrieval, interpretation, validation, and sometimes action. So this is where the fit becomes clear. FHIR gives us the structured clinical data, the standard APIs, and there's a lot of them in FHIR, and meaningful resource relationships. Agentic AI gives us reasoning, orchestration, and the ability to work across several tools in a sequence. Put together, you get a system that can translate a natural language request into structured retrieval, meaningful interpretation, and output that's useful to humans. Let's broaden the discussion a bit. I want to make sure everyone is grounded in the core agent concepts before we return to FHIR-specific patterns. At a technical level, an LLM is a probabilistic model that predicts the next token, or you think of it as word. That sounds simple, but the behavior that emerges from training at scale is powerful. Reasoning, summarization, transformation, and instruction following. At the same time, an LLM is stateless by default, has no built-in connection to your system. So architecturally, it's better to think of an LLM as a reasoning primitive and not a complete solution. A system becomes agentic when we put the model, the LLM model, inside a control loop. The model can plan, select tools, observe results, maintain intermediate state, and decide whether another step is needed. That means we move from one-shot inference to multi-step execution. The important point is the agent is not just the model. It is the model plus the loop, plus tools, plus constraints, plus state. It's helpful to distinguish these patterns clearly. A prompt is a single turn. Ask a question, get a response. A workflow is multi-step, but the path is predetermined by the developer. An agent is different because the model decides the next step, chooses the next tool, and adapts after seeing results. That distinction matters because not every LLM application should be called an agent. In this workshop, FHIR appears as one of the tools and data sources an agent can use. When we hear the word agent, they often picture only the LLM model, as I've said. In practice, an enterprise agent is a coordinated system. It starts with a user request, which becomes the goal. The model or planner decides what to do next. Tools and connectors provide access to the outside world. State and memory keep track of progress. Policy and approval layers govern higher risk actions. And then you have logs, evaluation, and monitoring that make the system observable. A good rule is to start simple and add autonomy only when it genuinely helps. Agent behavior is most useful when the task may take several steps. The path is not fully known in advance, more than one tool may be needed, and new information can change the next decision. And we'll see this in the second half. If the task is just one lookup or one deterministic business rule, a simpler workflow is usually the better design. This diagram shows the enterprise loop more explicitly. A request comes in, the model forms a plan, tools return evidence from the environment, and the agent continues until it reaches an exit condition. Around that loop sits guardrails, validation, approvals, logging, and evaluation. The key point is that this architecture is not specific to FHIR per se. It's rather the knowledge layer inside a more general agent pattern. Autonomy is rarely all or nothing. Most real systems use graduated autonomy. The agent may read and summarize safely, recommend a next step, and draft an action for review. But when the action can change clinical data or affect care operations, policy checks and human approval become essential. This is not because healthcare is uniquely anti-automation. It is because higher consequent actions deserve stronger control and better auditability. A realistic agent architecture assumes that failure will happen. The question is whether the failure is safe and visible. Agents may choose the wrong tool, work from incomplete data, get stuck in loops, misread an ambiguous request, and attempt something they should never do automatically. Each of those failure modes needs a design response. Clearer tool boundaries, evidence checks, max turn controls, clarification prompts, approval gates, and logging. Good systems are engineered for recoverability, not just success. Before we go deeper into FHIR, let me share a healthcare example that does not require any FHIR knowledge. Imagine a referral intake. An incoming fax, PDF, or email arrives. The system extracts the key fax, checks policies or routing rules, drafts the next step, and asks for human review when needed. It's easy to understand the pattern. Let's see how FHIR fits into the same overall architecture as a structured clinical data layer. Here's a picture of our architecture. The point is not to memorize this diagram, but to see how the reasoning layer, the tool connector layer, and the healthcare data services fit together in a coherent workflow. Agents don't do everything themselves. They rely on tools. These tools may be APIs, databases, search systems, vector indices, terminology services, or file servers, which we'll see a lot of later. The model decides, the tools execute. The separation of concerns is one of the most important design ideas in this workshop. When the tools are clear and well-bounded, the prompts become simpler and the whole system becomes more reliable. This is the core execution loop in practice. Reason, act, observe, and repeat. The agent interprets the request, chooses the next tool, executes the step, inspects the results, and decides whether another step is needed. From a developer perspective, this is closer to a state machine with feedback than to a chat interface. That loop is what enables iterative refinement, tool selection, and error recovery. As the system grows, one general purpose agent tends to become brittle. Sub-agents help by narrowing scope, and we'll see this in the demos. You can have one sub-agent for retrieval, one for terminology resolution, one for summarization, and another for workflow orchestration. That improves modularity, reusability, and testability. A useful analogy is microservices, but for reasoning tasks rather than traditional business logic. The Model Context Protocol, which you may have heard of, or MCP, is not an agent. MCP is a connection standard that helps an agentic application discover capabilities, request context, and invoke tools in a consistent way. Framed simply, it's a standard connector layer between an AI host and an external system. In healthcare, those external systems might include FHIR repositories, terminology services, search layers, policy engines, or scheduling systems. So, two common questions frequently arise. Who introduced MCP and why did it need to exist? Well, Anthropic introduced it in 2024, so it's not that old. The practical problem the AI community faced was integration sprawl. Every host talking to every tool through a different custom connector is expensive, brittle, and hard to maintain. MCP emerged to replace that fragmentation with a shared open protocol. The value is not just elegance, it's lower integration friction and better portability across hosts and tools. Healthcare agents rarely need one system, only one system. The useful agent may need structured FHIR data, terminology services, approval logic, policy content, search, and enterprise workflows, and we'll see that. MCP matters because it provides a more uniform way to connect those systems. It does not replace FHIR. It makes it easier to compose with FHIR and other services that these healthcare workflows need. Currently, our FHIR agent uses MCP to connect to a terminology-oriented service, but I would like to emphasize that terminology is only one use case. The larger takeaway is that MCP lets you standardize how the agent reaches external capabilities, whether that capability is code resolution, search, policy workup, or scheduling. When people first hear about MCP, they often reduce it to tool calling. The protocol is actually broader than that. It standardizes a lot of different interactions, including lifecycle, transport, resource, prompts, tools, and the way the host and server understand each other's capability. Well, this is a fast-changing area. The future trajectory of MCP suggests movement toward even a broader open ecosystem. So maybe next year you'll be seeing even better discovery, a growing server ecosystem. Certainly InterSystems is working in that direction with the AI Hub. Also more formal governance and stronger production readiness around trust and security. MCP appears to be moving from an early protocol into a much more mature ecosystem. So that sets the ground floor. Now let's return from the general agent discussion to the healthcare data layer. The central idea is that FHIR becomes the structured substrate the agent can reason over. Instead of asking the model to infer structure from text, we ask it to work with well-defined resources and relationships. FHIR gives the agent a predictable and queryable interface. It provides resource types, consistent RESTful FHIR API patterns, search parameters, and a standard way to retrieve and traverse clinical information. We don't have time to get into all the richness of the FHIR schema and the FHIR APIs. That's a long course in and of itself. But for the agent, FHIR becomes a tool with strong schema and meaningful semantics. The FHIR data layer, although complex, is more standardized than in many industries. Let's focus on the separation of responsibilities. FHIR gives the structure, the APIs, and the terminology bindings. The agent adds natural language understanding, multi-step reasoning, and contextual interpretation. FHIR does not answer the question by itself. The agent does not manufacture the data. Each plays a distinct role, and that clean boundary is what makes the architecture maintainable. Here's an end-to-end healthcare-specific view. The user asks a question in natural language. The agent receives it, resolves terminology as needed, calls the appropriate FHIR APIs, gets the result back as a FHIR bundle or a set of resources, extracts the relevant structures, and then uses the LLM to generate an answer. This is much closer to a back-end workflow than a standalone chatbot. The summarizer pipeline, which you'll see in a little bit, is a concrete implementation of this architecture. First, we retrieve the patient record, often using the FHIR operation $everything. Then we parse the bundle. Then we extract the clinically relevant features. Only after that do we pass the structured content to the LLM. The key design principle is that we do not send raw FHIR to the model if we could avoid it. We transform it first. Now, for some of you who may not know much about FHIR, FHIR computationally is a complex directed graph. There's over 150 different FHIR resources. They're all atomic, capturing some amount of clinical data. And they have links between them. But these links aren't fully populated. They are one way. So let's take a simple example here. Here's a graph that's showing just one specific FHIR resource, a FHIR patient resource, Ida Brown. And as you could see from this, she has a couple of observations pointing to her: smoking status and blood pressure. She also has a general practitioner, and she's pointing to that. And that general practitioner is part of an organization. This is how FHIR is organized. This is not part of anything dealing with agents. This is the FHIR its root organization or schema level. But now consider this. In a real case, with a real patient, we're going to have many, many more edges to this graph and many more resources. So in Ida Brown's case, we're going to have all kinds of conditions, medication requests, encounters, observations. We have to navigate this graph. If we want to summarize what's going on with Ida Brown, and we have FHIR as our repository of record, this is what the agent is going to have to work with. In fact, if you look inside the Iris for Health Community Edition and look inside the tables that make up the FHIR repository, what you'll see is you're going to see a lot of different tables that contain JSON data, just like I'm showing here. This is how the system is encoded, the FHIR schema is encoded within the FHIR repository. So FHIR, we want to be the data layer using a structured knowledge graph, using its structured knowledge graph. $everything, which is a FHIR operation, can give rich longitudinal context, but raw FHIR is not automatically LLM ready. And terminology codes carry much of the meaning. We'll talk about that in a little bit. Additionally, if code resolution is wrong, when the agent makes a FHIR query, is likely either to get no results or the wrong results will be returned. So it's kind of important to get those codes correct. So we need to construct a bridge layer between retrieval and reasoning. We parse each resource type, group the content into clinically useful categories, normalize details, such as units and status, and assemble this compact representation that's easier for the LLM model to use. The domain-specific data is optimized then for LLM input and reduces noise, lowers our token cost, and we'll get to cost in a little bit, and usually improves accuracy. So this is really where things become somewhat difficult for LLMs. Terminology is where many otherwise promising systems begin to struggle. Users speak in free text. FHIR queries require standardized codes. And the mapping from one to the other is often ambiguous and context dependent. Terminology normalization is difficult because it's not just a lookup problem. It is a semantic resolution under uncertainty problem. The system has to interpret what the user meant, map the meaning into the right vocabulary, and do so in a way that preserves clinical intent. That is why this often becomes the intelligent bottleneck in an agentic FHIR system. There are three core reasons why this is hard. First, free text is ambiguous. Second, multiple vocabularies exist for different kinds of concepts. Third, context changes meaning. If a user says diabetes, do they mean type 1, type 2, gestational diabetes, or are they referring to the broader diabetes concept? The system has to decide, and that decision directly affects the correctness of the retrieval. Here is the terminology ecosystem that our agent has to navigate. SNOMED CT is commonly used for conditions and clinical findings. LOINC is commonly used for observations and laboratory tests. RxNorm is commonly used for medications. The agent, therefore, needs to know both which vocabulary fits the concept and how to query it effectively. So here's SNOMED CT. It's systemized nomenclature of medicine clinical terms. It's a comprehensive, concept-based clinical terminology used to represent diagnoses, findings, procedures, body structures, and more. It's designed as an ontology that's hierarchical. In FHIR, SNOMED CT is commonly used for coding conditions and clinical concepts, and that enables precise and interoperable representation across systems. However, SNOMED CT contains on the order of 350,000 active concepts, with many more descriptions and relationships, making it the largest and most expressive of the major clinical terminologies. LOINC, which stands for Logical Observation Identifiers, Names, and Codes, is the standard for identifying laboratory tests, clinical measurements, and observation. Each LOINC code represents a fully specified observation defined by its attributes, such as the component, what it was measured, property, timing, system, meaning the specimen, scale, and method. It's widely used in FHIR for coding observation resources, especially for labs like glucose, creatinine, or hemoglobin A1C. LOINC enables consistent exchange of results across lab and health systems. Even when local test names differ, the LOINC database can be, if you use it and map to it, you could have semantic interoperability. But there's approximately 95 to 100,000 active terms. So it's very comprehensive, but it's also complex. The last major vocabulary we'll talk about is RX norm. This is maintained by the U.S. National Library of Medicine, and this provides normalized names and identifiers for clinical drugs and drug delivery devices. It links together various drug vocabularies and supports interoperability that's used in prescribing, dispensing, and medication history. RX norm concept represents ingredients, strengths, and dose forms, and includes different term types such as the ingredient, the semantic clinical drug, and branded drug. In FHIR, RX norm is commonly used for medication and medication request resources. RX norm contains roughly 100,000 active concepts. So it's also a very complex clinical vocabulary. So this is what the real flow looks like in the system. The user provides a clinical phrase such as type 2 diabetes mellitus. The terminology service then will return several plausible candidates. The agent must choose one. That choice is not a detail. It determines what data gets retrieved, which patients are included, and what conclusions the system can reasonably draw. So if it makes a mistake, it may return nothing. Here's the practical consequences of code choice. If the agent chooses a concept that's too narrow, it might miss relevant patients. So if it chooses, instead of type 2 diabetes mellitus, type 2 diabetes with ulcer, or type 2 diabetes in obesity, those are valid codes, but there may be no patients in the FHIR repository with those codes. So if it chooses something that's too broad, well, then it may pull the wrong cohort back if you're making a query. So terminology selection is essentially a precision versus recall trade-off, but in a clinical context where the stakes are higher. The point here is that the selection step is where most of the intelligence lives. Retrieval may be straightforward once the code is chosen, but getting to the right code requires reasoning, context, and sometimes restraint. If the code is wrong, the FHIR query is going to be wrong, and everything that follows will be suspect. So production systems usually need heuristics rather than a single hard-coded rule. If the intent is vague, the system may prefer a broader concept or ask for a clarifying question. If the context is specific, it can choose a narrower concept. It may also use patient context or task context to improve the decision. So the message is that the terminology resolution is a part of the reasoning layer, not a side utility. A practical architecture, which we use, uses a terminology service to generate the candidate concepts, rather than hard coding the mappings. The terminology service provides the options. The agent then decides which option is best or decides that more clarification is needed. So there's a very clean division of responsibility. The service supplies the candidates, the agent supplies context and judgment. Context-aware resolution is what moves us beyond static mappings. The same term may need different handling depending on user intent, surrounding language, or clinical context. When the agent can incorporate that context, the result is more accurate. The demo I will show in part 2 uses an open source MCP server for terminology resolution that in our case we are primarily using to map terms for FHIR search. Now, one thing I'll point out before we get to part 2, this MCP server has been blocked for SNOMED resolution. In the code that I've given you, I have a fallback system to a limited SNOMED subset, but it works very, very well for LOINC and RX norm processing. Once the agent has selected the concept, it still needs to convert that concept into the form a FHIR search expects. That usually means a token in the form of system, bar, or delimited code. So this is what we call a FHIR token. We start with the system. In this case, you're looking at the system of SNOMED CT, but in other cases, you may be looking with RX norm or LOINC. And then the code comes after the bar delimiter. So at this point, I'm going to connect some of these ideas so we could zoom out a little bit to understand what a FHIR summarizer can do using all these pieces parts we've discussed. The FHIR summarizer is just an implementation. It's a practical implementation and a reusable use case. It starts with raw FHIR data and should end with a structured clinical summary that you could read easily. So we're wanting to turn a large, verbose, machine-oriented bundle that I kind of showed you inside a FHIR repository into something clinically legible and LLM-friendly. So in this case, a subagent is a great tool for operating underneath the agent because it's specialized. Instead of letting a general purpose agent do everything, we create one specialized subagent to perform narrow jobs: retrieve, parse, extract, and summarize. The narrower scope usually improves the predictability, reliability, and debugging of the subagent. The summarizer subagent retrieves patient data, extracts the key clinical features, reduces the size of the data, and produces a structured representation. And then it feeds it to the LLM. In other words, it is the bridge between raw FHIR and useful AI reasoning. So this is not a general purpose agent. It has one defined goal: this limited context of summarizing a clinical patient set of FHIR resources. Even though the summarizer is specialized, it still follows the core agent loop. It plans within a narrow scope, calls its tools, processes the results, and continues until it reaches the goal. The FHIR summarizer has 5 stages: retrieval, parsing, feature extraction, data reduction and LLM reasoning. The first step is to retrieve the patient record. So it needs to use a tool for this, and that tool is the FHIR_everything query using the patient ID. Under the hood, it calls the $everything request, and the response is a raw FHIR search set bundle and a broad longitudinal view of the patient. Once the bundle is retrieved, we parse the raw JSON and turn it into more structured internal objects. We normalize the shape, group-related data, and prepare it for feature extraction. At this stage, nothing especially magical is happening. It's just disciplined data engineering. Now we decide what matters clinically. We pull out active conditions, recent labs, medications, key encounters, allergies, and other high-value facts. Just as important, we ignore administrative noise. This stage largely determines what the LLM will be able to reason over later. After extraction, we compress the information further into a compact structure. The goal is not to lose clinical value. The goal is to reduce redundancy and noise so the model sees a small, relevant, token-efficient input. This is where the system becomes both cheaper and more scalable. So let's take a look at that. Token management matters when you're going to be paying for it, not in the workshop here, but pulling back bundles, large bundles with huge amount of, let's say, JSON data may not be very cost efficient. By extracting the information from that JSON bundle, you could reduce the token count that the LLM will need to process. And that really does make a difference. You'll see it later as I demo this. We could reduce several megabytes of data to 16,000 tokens. That's about 20 cents for the GPT 4.1 mini model. After that, we could do a structured summary. In this stage, the model is no longer doing any search, filtering, or inference. It could do what it's best at: interpretation, summarization, and explanation. So what has the sub-agent actually accomplished? It identified the relevant resources, extracted the right fields, ignored low-value content, and produced concise output. This is more than formatting. It's structured clinical reasoning over a constrained data set. Let me say one word about the system prompt. It's much more than a style instruction. You may have built other systems with a system prompt. It, in this case, defines the operating model for the agent. In our implementation, the prompt is assembled in layers, starting with identity, then tool guidance, then security, developer instructions, user instructions, memory, FHIR-specific rules, and operational guidance. That means the prompt is acting as a policy service, not a personality service. The practical value is that the prompt can force consistent behavior around terminology resolution, reverse chaining, sub-agent delegation, and output formatting. That matters because FHIR questions are often ambiguous in natural language, but the downstream operations must be precise. So the prompt becomes the bridge between messy human intent and structured clinical retrieval. Good prompt design should follow this layered architecture. Not all instructions belong at the same conceptual level. Identity tells the model what role it's playing. Tool guidance tells it how to think about available actions. Memory provides continuity. FHIR-specific rules are inserted near the end, so they are close to the final decoding context. So healthcare agents often have both general and domain-specific instructions. Here's how we turn a prompt into a safe reasoning path. The sequence of our system prompt encodes a mandatory order of operations. First, the agent must classify the clinical domain. Then it must use MCP terminology tools to resolve the natural language term into a standard code. Then it checks whether the answer may already exist in code examples or cache patterns. It uses reverse chaining when necessary, so the FHIR query is constructed correctly. Only after this is it allowed to call FHIR_search. So good prompt design can reduce both hallucinations and inefficiencies. As we discussed, the main agent should not do everything itself. In our system prompt, summary requests are explicitly routed to the sub-agent FHIR summarizer. The main prompt should own orchestration concerns, understanding the user request, applying safety rules, deciding whether the task is retrieval, terminology resolution, summarization, write approval, and then sending the work to the right tool. The sub-agent prompt, on the other hand, is narrower and more detailed. A good FHIR system prompt is explicit, layered, and testable. It tells the model how to route work when terminology resolution is mandatory and when a sub-agent must be used. Before the break, I want to clarify vocabulary. A tool is a single action, such as a FHIR read or terminology lookup. A skill sits one level above it. It packages a repeatable way of using one or more tools with the right instructions, scope, safety constraints, and expected output. A sub-agent then is a specialized worker that may execute one or more skills as part of a focused task, such as patient summarization or terminology resolution. Finally, the broader agent is the orchestrator. That's the person who decides, or the LLM decides, when to call what capabilities. In part 2, we're going to move to the demo side of showing these in action. And as I've mentioned, this is an open learning tool. It's built entirely on Python. So there's no commercial code here at all. You could download it from the internet. You could see here's the GitHub repository, or you could copy it from those flash drives onto your laptop. Please return those to me though at the end, because we need them for the next session who may want to also operate some of this code. So this is entirely educational. I'm going to be demoing all these things in just a few minutes here. So with that, we'll take a break and I'll take any of your questions. And we'll come back and maybe, 15 minutes, I think we could do it. Are there any questions on part 1? Yes? On your last slide, I was confused by the difference between skill and sub-agent. Let's go back to the last slide here. Are we talking about this slide? This. You want clarification about the skills in Agentic FHIR? About sub-agent and agent. Okay. An agent is a broader... Sorry, about sub-agent and skill. Yeah. A sub-agent is a... Think of it as a type of agent that has access to repeatable patterns of tools and instructions. So it's in some ways has some of the same characteristics. The difference between skill and sub-agent can be somewhat arbitrary. But the idea is a skill can include more than just tools. It can include things like instructions, like prompts that guide the sub-agent in its various tasks. So this is a little, I agree that there's a little bit of semantics here that make it less than 1,000,000% clear where that boundary line is drawn. So there's no real hard and fast rule here. Okay? Do we have some other questions? Let's get started here. This is what we're going to cover in the second half. We're going to be focused strictly on the execution. We're going to talk about how that agent retrieves data from the FHIR repository, how terminology feeds into search, how the bundle becomes a compact summary, and what safety and production concerns appear when you move from a demo system like this is to deployment. So everything we've discussed so far depends on retrieving the right clinical data. So I want to have a section about the agent's tool set, how the agent chooses among these tools and how those choices map to concrete FHIR operations. These tools that you see on the screen are the agent's API surface. Some are narrow and direct, like FHIR_read. Some are more flexible, like FHIR_search. Some are broad, like FHIR_everything, that uses $everything. And some are composite abstractions, like the summarizer. The point is that the agent is not improvising against the repository. It's operating through a defined tool layer that you're looking at right here. So here, let's take a look at FHIR_read. And this is really the simplest retrieval pattern. If the patient ID is already known, the agent doesn't really need to do much reasoning at all. It just simply chooses the direct read tool and fetches the resource. It still has to interpret some natural language, but really not anything. So why don't we just see this in a simple demo? And actually, I'm going to combine this demo with another demo, FHIR_search, because they're kind of closely related. Here, we're going to try to find some patients named Smith or find some other different patients. We'll just select at random. Now, this whole thing is run in Python, and I've created Docker containers so you could use it even more easily than I'm using it in this development environment. But the first thing you're going to see is some general information about the AI agent. So we're using the GPT 4.1 mini model. You could use any model you want, really, but this is a cost-effective model. And there's lots of commands. If you want to find out more about what commands are available, we call them slash commands, you could just say /help, and this will show you all of the commands that are available. So you could see we got clearing the conversation history, approval mode, stats, tools, MCP, etc. Probably the most important command that you're going to use when you're using the system is the /config command, because that tells you a lot of important information about the system. This is saying we're using the GPT 4.1 mini model. The temperature, I'm not going to get into, but it's essentially set at the midpoint here. What our working directory is, how many turns, meaning how many times could the agent go through a loop? We're saying, hey, there's a maximum of 100. We're not going to get into hooks, but base FHIR URL. Well, this is critical because we need to know where that FHIR repository is if we're going to communicate with it. And this is set up through configuration. And we have a config.toml file that you can modify to point to other FHIR servers. We're using the R4 schema here. The other thing that you could see here is if we type /MCP, you're going to see that we have two MCP servers that we're connected to. This file system that does things like bash commands, etc., which we're not even using at all. It has 14 tools. And then this other very important MCP server, medical terminologies. This has 27 tools, but we're using just a fraction of those tools. So there's a lot of tools in medical terminology. I did not write it. It's an open source repository, as I've shown you. But here are the tools that we are using, including, well, these file system tools we're not using, but we are using FHIR search, FHIR read, FHIR update, FHIR underscore everything, the sub-agent FHIR summarizer, and these medical terminology tools. And I think I explained at the beginning of the workshop, this SNOMED search has been more or less disabled by SNOMED International. Next year we'll have some workaround to that. But in the meantime, I built a backup system with a limited number of terms that can be resolved to SNOMED. The other thing that you might find interesting is this command called /stats. And that shows you statistics about how much token use we've used. Well, now, why is this important? Well, because essentially you have to, in theory, when you have your own open API key or some other Claude Code key or whatever, you're going to be paying based on the number of tokens that you process in the system. And there's two kinds of tokens. There's really the input tokens or prompt tokens, and the completion tokens or the output tokens. And normally you're going to be charged based on the input plus the output and the total token count. So again, this is why you don't want to feed in, you know, megabytes and megabytes of free text data, even though the LLM may be very happy to accept that. It's going to, first of all, take longer to process, and second, you're going to be paying more money for it. Okay, so let's just give it a general command. Why don't we say something like this? Show me 10 patients in the FHIR repository. So it's got to go and get that data, right? It has to retrieve it. And so how does it do that? Well, let's go back up and take a look. It's got to create a FHIR query, and it's showing a lot of this bundle. Okay, so what it's doing here is it's correctly the agent correctly calls this tool, FHIR search, and it says, oh, I'm searching for patients because that's what was asked. I need a max result of 10, and here's the search I'm going to create. I'm going to create it to this base URL, patient, and underscore count equals 10. That doesn't mean we're limiting it to 10, by the way. It means 10 results on a page. It got a 200 response, meaning it was able to retrieve all the patients in a search set bundle. Notice there's 115 entries. And did it need to use reverse chaining? No, it did not. And it's showing you the entire bundle, except in this case, we're truncating the bundle just so it would make it easier to follow along. But then it does this thing here. It's doing a nice summary of this bundle, and it's showing you the IDs of the patients. So if we said, hey, I'm going to give me all the details on patient 7. Well, now it's decided, and notice it could have just given me the FHIR resources on patient 7. That's what I kind of wanted it to do, but it chose a different tool. And notice what it chose to do is use the sub-agent FHIR summarizer instead. So it's going to pull back a ton of data on patient 7 that includes not just the patient's the patient FHIR resource, it's going to pull back observations, encounters, medications. And notice it's taking a lot more time to do that because there could be, I don't know how many megabytes of data on ID7. So we'll let it go for a little while longer here. I don't want to terminate it. But this will give you an impression too of how you need to, at times, be much more specific in how you want to query things. Okay, so notice now it is creating this complete summary of this patient. And this is what we would expect it to do. The termination is the goal, or the goal was, it was completed essentially. The tool calls, it did a FHIR underscore everything, and it's now summarizing all that data in a nice format. You could see the active conditions, medications, etc. So if we wanted to be clearer about this, we would have to say, because it made that mistake, I would say, can you just retrieve the FHIR patient resource for patient 7. So this is trying to make it a lot more specific, a lot more, and this should just call FHIR search. So let's see how it handles this. Interesting. Okay. And now you see, okay, so now it's really pulling the FHIR resource, the patient resource for patient 7. And let's just confirm by going up here that it did a FHIR read operation. So this is the simplest operation to use. We're reading resource ID 7, but it turns out that that's resource type patient. And we're pulling back this FHIR resource, not a bundle, FHIR resource. And here's what it looks like in JSON. So it's doing exactly what we asked. Now, most of the time you're going to be faced with you don't know exactly FHIR IDs or anything. You really need to do some kind of search. So what do we ask about this? What if we say, are there any patients in the FHIR repository with the last name of Larson? And great, it finds that there's one patient in there. And if we look at this, we could see that it created a query string. Now this is what you would have to do if you were using the FHIR API. What you would do is you would get the base FHIR URL, which we have from the configuration section. We'd say underscore name equals Larson and account. Here it's saying 10 per the page. Okay, I didn't give it that instruction because it could be that there is more than one Larson in the system. How about if we wanted to construct a slightly more complex query? Could we say something like, let's go back to our patients that we first retrieved. We had a bunch of patients there. And the nice thing is it's able to keep, obviously, the context of all of this. Well, here's a patient, Susan Mann. Okay, that seems like an interesting patient we could maybe make a quick query about. So how about if we ask this? Are there any patients with the last name of Mon and first name of Suzanne? I think she had two N's, I'm not sure. Okay, so yeah, it got that right. But how did that change the query? Well, now you see it had to construct a query with two different conditions. So the query string is slightly more complex. It now is including the given name. Notice we said first name, but the system is able to use its reasoning in natural language to know that first name and given is what is required by FHIR. So this is the kind of thing that the assistant is capable of doing. So let's go back into our slides. Okay, so we could see could we have done a Boolean query essentially with Smith and gender? Yeah, that would be very similar to what we saw with a FHIR query for Susan Mann. Would be no difference there. Okay, now we get into a serious problem, and that's terminology resolution. And this is where we need that MCP server. So we're going to try to resolve things like, hey, what would we get if we use patients with diabetes, and what could we get if we're looking for type 2 diabetes? Under the hood, we have to do what's called a search using a token. That token has a system and a code. So what system should we use? Should we use SNOMED? Should we use LOINC, RxNorm? Well, that's where the system has to know that diabetes is a clinical condition. So it's got to use the SNOMED system because this FHIR repository has all its codes for conditions in SNOMED. The other thing it has to do is reverse chaining. And I have a feeling a lot of you may not be familiar with it. Let me just talk very quickly about a token search. Token search is to match uncoded values where you know the system. And again, you have to specify the system. In the case of SNOMED, we're using, you could see the system is specified as http://snomed.info/SCT. And then we have to find the code that corresponds to the condition we're interested in. So for something like this, if we wanted to find all the observations, for example, find observations for glucose, and we had the code for it, let's say we knew it was already 2345.7, this is how we would specify that query. Get observation question code equals that system and that code. So reverse chaining is where what we start with is we're interested in patients that have a condition, or we have one FHIR resource that points backwards to another resource. And in this case, we use a different kind of query string and a different kind of query format. So we use the _has, where in this case, we would get the condition, we want the patient and the code for that condition. So this would be, for example, find all patients who have type 2 diabetes mellitus. So here is the syntax as needed. This is what makes FHIR and FHIR APIs a little bit complex. Where can you find this information? Well, it's all available on the HL7 FHIR website. But each resource has their own specific search APIs. So you have to use it correctly. There are some of them that have the exact same API, but many of them don't. So what does the agent need to do to basically resolve queries like this? Well, it has to extract the concept, resolve it via MCP with that terminology service, build this _has query, and then it has to execute the search. So a fairly complex set of flow here, number of steps that it has to do. And it has to make those choices based on the prompt we gave it. So why don't we do this? Let's go back to our demo screen and let's see if we could find patients with conditions and find patients with allergies. All right, so let's try a query here. I'm going to ask it find all patients in the FHIR repository with type 2 diabetes. Now, I'm going to point out a few things here. Okay, so it found 6 patients. Let's take a look at what it had to do to find those patients. So it's returning a search set. The first thing it had to do, notice the agent had to call this tool, medical terminologies __ SNOMED search. Now, as I've mentioned to you at the beginning, we're being blocked. Our MCP tool is being blocked, or external MCP tool is being blocked because of SNOMED. But I built in a workaround for a limited set of about 100 different clinical conditions. So it's using the fallback code that comes from this in repo lookup table. But in any event, it called this, and when it only when it failed, when it saw that it couldn't get this error, when it saw it got this error, 410 error, that is an indication of that block, notice it had a fallback position. And this is something you should consider in the design of your systems, because it's going to invariably happen that your agent will call tools that won't work. So what is your fallback position? In this case, we have a local tool set. It's not as good as clearly a full terminology server. But it was able to do the following. It was able to pass that information onto the FHIR search tool, where it's saying, okay, the clinical domain is condition, the resource type I need is patient, and the resolved token I've computed, and it turns out it computed it correctly, is this SNOMED code. And then it built this query. It used the base agent, and then it built essentially a reverse chaining call. And it found 6 patients. And then it returns a search set bundle. Perfect sense. Now, it took from that bundle and summarized that data pretty well. Let's see if we get to the end of this here. Yeah, we only asked it for the patients, and so it gave us the name, gender, date of birth, and the ID of the patient. And we could get more details on any of these patients if we want. One of the things we should do is, why don't we do a stats query? See, now we had one summarization, so we know we're going to, our token count's going to definitely be going up here. So we've used 304,000 input tokens, still fairly modest, and a total of 306 total tokens. Again, how much have we cost? Probably around 30 cents or so. So not bad, okay? Let's try something else here. How about this? Find all patients with allergy to peanuts. So we want to create a different cohort. Again, it doesn't have the SNOMED system through the remote API, so it has to do it locally. But again, it's generating the search set bundle. The key thing here is to see that it knew the correct clinical domain, and it knows that allergies in this repository are coded towards SNOMED. So it used and did a SNOMED lookup. Again, it had to use the fallback because it couldn't go outside. It got back that bundle, and then it was able to get and create this nice summary. So this is a good example of how FHIR search is used and how a reverse chaining FHIR query can be constructed. So this is kind of useful if you're getting just started with FHIR search. All right, so we've seen a little bit of how you could do a comprehensive patient summary. Well, and we'll see another example. But to get that information, we're doing under the hood a $everything request that's returning a complete longitudinal record, a big bundle that could contain hundreds of thousands of resources. So we need to filter that to some degree to input into the agent a smaller data set. $everything gives the agent a very comprehensive starting point. Another thing that we could do is we could do more than just retrieve data. We could update data as well. So up to now, the examples I've shown you are read-only. And I would like to emphasize that agents can do more than just read. They could update clinical data. But in this case, the architecture must change slightly because approval, traceability, and strong controls become much more important because the system's no longer only observing the record, we're actually changing the record. Get the top 10 medications from the repository. Okay, no, actually, this is actually a correct result. There are no medications in the FHIR repository. What should I have said? Because medications is a resource type, but really what I wanted to say is get the top 10 medication requests from the FHIR repository. We have synthetic data, Cynthian data in this repository, but we don't have any medication resources. We have medication request resources, though. All right, so we see it produced the bundle. And notice, again, in terms of intent, if you use medication to meet medication requests, you're going to be disappointed. But let's take a look at this. We have this medication 10, simvastatin 10 milligram oral tablet. It is stopped. So let's make it take an action to change that. Can you update medication request 10 from stopped to active? All right, so medication request with resource ID 10, status active, status is stopped. Now notice something that you haven't seen so far. This is a request that has been by policy tagged as something requiring a human approval. So when we get into riskier operations of creating data or updating data, we need to bring the human in the loop. And we do that through the use of policies. Policies are built into the system so that any FHIR update or FHIR delete or operation, and we don't have, I didn't build any tools for a full FHIR create, although one could build that. And probably you'd want that to also have by policy need approval required. So I'm going to say in this case, I'll go ahead and say yes, I approve that, make it active. Oh, notice it does not have, it misinterpreted that ID. So ID 10 does not exist in the repository. So the first thing we'd have to find out for this specific update, we'd have to find out what corresponds to this simvastatin 10 milligram oral. Okay, so let's say, why don't we do something like this? Provide the first 10 medication request resources. FHIR IDs. Okay. Right, medication request. So let's try that again. Just say 5 medication request. Yeah, see, any kind of ambiguity here. So I said sources, and what I meant was obviously resources, right? But that matters. It definitely matters. Okay, so here I have now retrieved resources, not sources. And I could see here on this ID 53, I have a status of active. So I'm going to say for medication request with ID equal 53, change the status from, and it was active, right? Yeah, from active to stopped. Okay, and let's see if it does this now. I'm going to say, yep, I'm happy with that. And there it used the FHIR update operation. Notice we got a status of 200. So this update did happen, and we could, we could query for it. So obviously when we're modifying clinical data, we have patient safety, legal, and audit implications to this. And so these should never be treated as equivalently to read operations. So updating a medication dosage, changing a diagnosis, adding allergy information, or deleting data are all consequential actions. The point is that agents should never support these workflows without a human in the loop. They require explicit approval and the model should get that approval prior to making any changes. So this is where we get into an approval policy. An approval policy defines when approval is required, who can give it, and what must be logged. That includes the trigger conditions, the affected resource types, the operation type, the required approval role, and the audit record. So this is what we call the governance layer that separates it from the model itself. And this is the full human-in-the-loop flow. The agent proposes the right, the policy layer evaluates it, a request for approval is generated if needed, and then the human either approves or rejects. All right, now we're going and looking directly at this summarization problem. We're going to connect retrieval, terminology, and transformation into one complete workflow. And once we have the data, how do we make it useful? So this is how we bridge that from the large bundles to user-facing summaries. So the overall flow is retrieve, structure, summarize. The critical middle step is often the part people skip when they are new to this space. Retrieval alone does not make the data usable, and asking the model to summarize raw bundles directly is usually inefficient and noisy. So I'd like to stress that the summarizer is defined as a subagent, not a loose prompt. And so you're looking at some of the code here. It has a clear goal, a constrained tool set, a defined scope, and a predictable return path to the main agent. So it's much closer to a controlled execution unit than a free-form chat. So here's what it looks like in that sub-agent prompt. Step one is telling the summarizer how to read the bundle. We explicitly give it instructions to focus on these specific resources: patient, condition, observation, medication request. Because the summarization quality will depend on it identifying these things in the bundle. Then step two is feature extraction. We define the categories we want to pull out. So demographics, active conditions, medication encounters, observations, and allergies. So we're defining essentially the schema for our prompt. We're telling the model what the structured output should contain. And here is where we give it the formatting instructions. We're giving it the output structure. We specify how those sections and format of the summary should look like, because we want our summaries to be consistent. And then we have some anti-hallucination rules. We explicitly tell the model not to invent data, to summarize only what is present, and to say not available when information is missing. So this is all very important in prompt design. And notice we also are telling it what are the allowed tools. So notice it can only use these two tools, FHIR_everything and FHIR_bundle extract. So we're not, and giving it a max turn of 8. So we're really giving it some limits here. So these are things that why you want to look at this. Well, you're going to have production concerns in terms of latency, token cost, repetitive terminology lookups, compliance, and observability. All of these are what makes really for an effective application versus just doing a demo here. Create an effective clinical summary of patient 1. So it now has the goal. It knows it needs to use the sub-agent. Good. but it's got a lot of work to do under the hood. It has to call the tools, FHIR dollar everything. It has to call the FHIR bundle extractor, and then it has to format this. So, as you could see, it does all of those things. Stuart Larson has its conditions, medications, etc. And we could ask it. One of the nice things, of course, we are emphasizing the FHIR, but could we say to it, what would you recommend for preventative treatment, let's say? Should be tailored by a healthcare professional. I like that. But they would want consistent adherence to the anti-epileptic medications prescribed, regular neurologist follow-up. I am a neurologist, so I'm happy with that too. So this is the kind of thing then you can expect with a summary. I'm going to just say a few things about design patterns, safety, and production concerns. The LLM should be your reasoning layer, and you need to build tools. The more tools, the better. Obviously, if you more sophisticated tools might cover a larger service area. So you need tools for FHIR retrieval, terminology resolution, and summarization. Better tools usually mean simpler prompts. Subagents help you control complexity. I think we've seen that pretty well today. The decomposition usually improves reuse. And not only that, it reduces hallucinations, makes the system easier to test. You also want to limit the system to have least privilege access. Agents should only start with read-only access. Really work your way up to this write access, because they're basically, it can cause a lot of mischief. Even when the LLM output looks plausible, it may still be wrong. So structured validation provides a post-generation safety net. Part of what we do in validation of this system, notice, when it makes a FHIR query that's wrong, if it violates the schema, it will basically know that it's made a mistake, and you'll know it too. So you'll obviously make your query better. But one of the things you have to keep in mind is that even if it passes schema validation, it could still make a semantic error. It could make a coding error. So you may need to check that. Logging is important because you would like, in any production system, to keep track of these MCP resolutions, FHIR queries, what codes were selected by the system, etc. And again, this whole thing, you have to design for failure. So you're going to have retries, etc. So at this point, if you want to learn more, you want to go deeper, I want to point to you some additional information. One of the things is that there is a working group called AI Transparency on FHIR that you might be interested in. If you're in FHIR research especially, there is an official working group for this, and I think they may appear at Connectathons. InterSystems itself is creating a new AI hub capability that you could learn about this week. This will help you build AI apps and agentic workflows. This demo I'm building here did not use the AI hub. It wasn't ready yet. But you could learn more about this during the week, and I would encourage you to explore that if that's your interest. And we have a lot of different sessions that you might be interested in. One tomorrow on Firestore and AI Accelerator, transforming a chatbot into an AI agent using Iris for Health, multi-agent orchestration, agentic engineering live on stage, AI and interoperability, InterSystems Iris, interop and agentic agents, and building AI apps and agentic workflows faster with the AI Hub. That's one of the things you might want to check out. If you're interested in FHIR and you want to go deeper on FHIR, we offer a course of 45 hours, beginner, intermediate, and advanced. You could easily sign up. Here's the link to that. I built a training website that's accessible for this course, so you could learn FHIR to your heart's content, and it covers AI agents. As you would well guess, there's a number of lessons on AI agents. Right now, I think it's about 4. So that's it. I hope you enjoyed this, and I'm open to any questions. Are there any questions, or did I go over everybody's head? Well, okay, yes, when you say variations, there was a lot, the question is, yeah, go ahead, let's have them repeat the question.
So the question was if you tried variations of the LLM that you used to tie everything together, different models.
I didn't, okay, so when we talk about models, I only used GPT 4.1 mini. That was the only model. But the prompt design, the tools, the workflow was all a result of a ton of experimentation. So I didn't just come up with this and, one day, coming into the office and saying, oh, I think I have this all solved. No, it was a lot of experimentation. I think that as you'll see over time, this will become more standardized. Right now, we're in kind of the early, very early stages of this, where I think there's a lot of experimentation needed. And we have to look at all the use cases. I built the system where I thought people would like to learn about how to use FHIR APIs and a few interesting things with FHIR summarization. But this is by no means, this is just scratching the surface. So this audience will be providing all the incredible new applications next year, right? We're going to all come back and we'll have a lot of innovative applications, and I'll just be smiling and watching you from your seat. Any other questions? Okay, very good. Thank you very much.